An alpha decay occurs when a large unstable nucleus gives off 2 protons and 2 neutrons. Now what is left afterwards is a different element. In some situations it will be a stable isotope, and so that will be the end of any radioactivity that's going to occur. But just sometimes the only thing it can turn into is another unstable isotope of a different element. That happens with thorium, a heavy metal sometimes used in gas stoves. Thorium turns into radium. Not all at once, but atom by atom they start changing from a thorium atom into a radium atom by getting rid of an alpha particle. What then happens to the radium is something amazing. It gives off yet another alpha particle, and in the process it becomes radon. Now radon is very different chemically to thorium and radium. Thorium and radium are quite happy to be chemicals mixed in with other chemicals, forming a solid that you could physically see and touch that you would want to. Radium is a noble gas, and so it doesn't form chemistry with anything. And so as soon as that radium turns into radon, it becomes a gas and it escapes from the solid structure. This is what is happening beneath our feet. This is what is happening to produce the radon that we detect in the background radiation. Radon is produced by the process of releasing an alpha particle. Now those alpha particles that are released, if we measured those, it would tell us something very interesting about that particular decay. So here we have a sample of thorium. It's a thorium gas mantle. This is a device used in a camping stove to get a nice bright flame. But this little mesh here is impregnated with thorium atoms. Now some of these will have already turned into radium atoms, but you can't tell because they're mixed up all together. It's just a mix of atoms, an alloy if you like. But 1 or 2 of those radium atoms are going to be again decaying into radon, a gas that would slowly fill this packet. And that is what we're going to look at right now. So what I have here is a really cool device. In here we've got a couple of those thorium gas mantles. And what I'm going to do is I'm going to allow some of the radon that is being given off by them to get trapped into this chamber that's going to look at that radon and then measure any alpha particles coming off it. So here we go, we're just going to pump some in, and we just need to get a good amount in, and then we're going to trap it so that no more radon can get in there. And we're going to measure the amount of alpha particles detected in this chamber. Now if I had not clamped it like this, then fresh radon would continually be going in, and it means that the amount of radioactivity coming inside this chamber would be about constant. That decays were occurring, but fresh radon was going in after it. By clamping it off, the radon that's inside there is now a fixed amount. And what is happening is they are starting to decay. Now, radon gives off an alpha particle and produces lighter elements. It actually gives off an alpha particle becoming polonium and then eventually to lead. And when it becomes lead, it has become stable and it no longer gives off any radiation whatsoever. It means that our radon gas has become lead atoms, one of the heaviest metals that you can think of. It's an amazing transformation. But what we can do is we can measure how that goes. Now I've set this detector here and it's actually measuring the amount of alpha particles present in the chamber from that radon over time. And what it is going to measure is over a period of about 10 minutes, just how many alpha particles are in that zone. So we'll sit here patiently and we'll see what the results look like. So there we go, we've been running now for about 6 to 7 minutes. And what you can see from that red line is the amount of alpha particles being given off by that radon gas is going down. In fact, it's going down really rapidly. Very rapidly to start with, but perhaps less and less rapidly as time's gone on. Now this is a very important graph because what it shows us is that when we have a fresh sample of radon, there are a very large number of unstable atoms that could decay, meaning that in those first few moments there is a very high rate of decay going on, lots of alpha particles in that time interval being created. But as time goes on, there are fewer and fewer radon atoms remaining, meaning there's less and less of them that could be giving off alpha particles, meaning that further on down the line, there are fewer and fewer alpha particles being detected. Here on a larger scale, we can see I've got my activity here, which is akin to the number of alpha particles I'm detecting every second, against the time in minutes there. And what I could do is I could say that after 1 second after 1 minute it was about 24, after 2 minutes it was approximately 12, and after 3 minutes it was about 6, and after 4 minutes it was about 3, and basically what was happening is we are plotting a graph that, though in reality would be a little bit jaggedy, on this axis would look like this. What is clear is that the 24 becquerels has gone to 12 becquerels in how long? Well, in approximately 55 seconds. And then what's happened is it's gone from 12 to 6, halving again in another 55 seconds. It's halved again to 3 becquerels in about 55 seconds. The nature of random decay is that half of your unstable nuclei will decay in a set interval of time. And it's the same set interval of time for it to halve again. Now we call this the amount of time it takes for half of your nuclei to decay, the half-life. So here's a really important question. Why does the alpha particles being given off in this example of radioactivity produce a graph that does that? Well, that same graph is produced anytime there is a random occurrence going on. So whenever you have a random situation, we see that same graph occurring. Now, I've got a very good visual model of this, and I'm going to write this down as we go. What I've got here is I've got a pot of dice, and I want to know how many times I get an odd number. And so I'm going to roll it many times. I'll draw my table here. And so we've got the roll number, and I want to count the number of odd dice. So here we go. Okay, so if it's not odd, then it goes back in the pot. So that's even, that's even, that's even, that one. So all of these should be odd, which they are. So how many have just decayed? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So the first roll, 23 of those decayed. Now, here we go again. How many of these are even? They go back in the pot. So there's even, there, and all of these are odd. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 more have decayed. So they're all gone. Let's go again. So we get rid of the even ones. Oh, just those two. So what we have there is 4 have decayed. Now notice, why is the number of decays going down? It's because there's less of them to decay. Right, here we go, last 2. Oh, they both go in, so none decayed that time. It is random, remember, so there is that chance that it just might not. Let's go That's a 1, that's a 4. Okay, so 1 decayed on the 5th roll. Oh, it survives again. It survives again. It's gone! My sample has completely decayed. Now, if we were on our graph like this, if we drew this, then what we would find is with the number of rolls down here, 1, 2, 3, 4, 5, 6, 7. So this is our number of rolls, akin to a time interval. If in every single time interval we rolled it again, then it's a very similar concept. And it goes all the way up here. So that's 5, 10, 15, 20, 25. So this is the decays, or let's call it the activity, the number of decays that occurred every second. And so this is the activity up here, and in becquerel. And this here is, let's say we rolled it every second. So this is the time every second. Time in seconds. To start with, we had 23, then we had 12, then we had 4, then we had 0, but then we had 1, and then we had 0 and 0. You can see that of all of these dice, however it started, it has drawn a perfect decay curve. Whoops, a decay curve. So that explains why we saw that graph, because the actual process of decay was a totally random thing occurring. But it is possible to have different half-lives depending on the chances of decay in each time interval. So here, in this experiment, I was looking for odd numbers would have decayed and even numbers would persist. But what if I was to repeat the experiment with only removing the number 1 and keeping the numbers 2, 3, 4, 5 and 6? What you realise is that rather than a half chance of each individual dice decaying in that time interval, there was only 1/6 chance. And so what you should expect to see is that the dice last much longer and they're not all gone after 7 rolls. Now this is true with radioactive nuclei. Some of them, they're much more active, and so they decay away much more rapidly than other substances. Some of them, when there is a lower chance of decay, actually persist for a long, long time. When the Chernobyl nuclear accident occurred, some of the unstable isotopes released into the environment were both very active, but also they had very long half-lives, which meant that they would be giving off radiation for thousands of years to come. The half-life of a radioactive isotope depends on the likelihood of any individual nucleus undergoing a decay. This first decay here, thorium turning into radium, has a half-life of 1.9 years. It means that in, well, about 2 years' time, my radioactivity of my thorium samples is going to have gone down to about half of its original value. And then in 4 years, it'll be down to a quarter, and so on and so on. Now, some different radioactive isotopes have different half-lives. This one here, radium turning into radon, happens every 3.6 days. So the production of radon is actually quite rapid. There's this radium takes a long time to form, but the radium very quickly then turns into radon. So at any given instant, I would have quite a lot of radon in an enclosed space, but not a lot of radium because it processes to radon quite quickly. Even more quick is how quickly radon then disintegrates and loses an alpha particle and turns into polonium and other things, and that has a half-life of 55 seconds. That's why with the experiment we did over there, over the space of about 10 minutes, all of the radon decayed and gave off its radiation and enabled us to form this graph. Now the kind of questions you might get asked about this would be of the following type. You might be presented with a set amount of time and be asked to express as a fraction how much of the original atoms are remaining. So, for example, in the case of this one here, the 55 seconds, if I was given that the time that we're interested in was 220 seconds, how much of the original substance is left? Well, we can work that out. What we need to do, if we know that the half-life is 55 seconds, then we need to work out how many times our number of undecayed nuclei have halved. So 220 seconds divided by 55 gives 4. There are 4 55s in 220. It means it's halved 4 times. So if my original number was 100, halving once goes to 50, halving twice goes to 25, halving 3 times goes to 12.5, and halving 4 times is 6.25. It's 6.25 from an original of 100. Now this is the same as saying it's a half times a half times a half times a half, or 1/2 to the power of 4. Half times itself 4 times. So what we can do is we can work out what original fraction, if I had 100 and I times it by 1/2 to the power of 4, you can see I get 6.25. In the exam, you won't have to do anything as complicated as that, but you will have to present what fraction of the original amount of undecayed nuclei remain once a certain number of half-lives have occurred.